Hello everyone. One of the topics that we deal with in statistics, or the biggest topic that we deal with, is equilibrium, right? That's when the system comes to the case that all of the forces and all of the moments the total of them is equal to zero. So the system does not move, or if it does, it is going to be with constant velocity, both translation and rotation. Most of the time when we are dealing with equilibrium in statics, the system does not move. And now the question is, if the system is not moving and is stationary, what's going to happen if we just give the system some small disturbance, some small motion, and move it a little bit away from the equilibrium? What's going to happen? Is the system going to go back to the equilibrium, or no, it is going to what? It is going to get away further and further from the equilibrium. So in the first case, we say the equilibrium is stable because it goes back to its original position under all sorts of disturbances in different directions, always go back. Otherwise, when it gets away and the distance between the current position of the system and the equilibrium gets larger and larger with time, we call it what? Unstable equilibrium point. So the question is, how do we determine the stability of an equilibrium point, right? And one of the, I guess, most famous cases of that is a pendulum, right? If you have a pendulum, if you let the pendulum come to rest, most of the time what you can see is the pendulum is what? It is going to be resting at when this angle theta is exactly equal to what? 0, right? So when it's perfectly vertically down, we say that is the equilibrium point. But you can also, if you can balance it perfectly well, and if the system is perfectly symmetric, you can also balance it here. When it's completely vertically upward, you can also balance it. In this case, if your base of measurement is still the vertical downward line, your angle theta here is going to be 180 degrees or pi. So there are two equilibrium points. There are 2 points for the pendulum, right? Either theta of 0, which we call it a regular pendulum, or the theta is 180, which we call it what? The inverted pendulum. And the question is, between these two, which one is stable, which one is not stable? Well, it's quite clear that in this case that the theta is 0. If I give it some disturbance and bring it, let's say, to this position shown with a color black, and let it go, let's say I give it some disturbance of, let's say, theta going from 0 to, let's say, 15 degrees to any 30 degrees, and let go, and it doesn't matter whether it's on the right or on the left, right? When I release it, ultimately it is going to settle down again back at theta of 0. If there is damping in the system, which there is always in nature, it is ultimately going to go back to theta of 0 and stops there, right? So we can say this guy is what? Stable. But in this case, that the theta is balanced at 180, it's just enough that I don't need to even give it a big disturbance. Just smallest deviation, just a fraction of a degree is enough, right? And when I do that in either direction, doesn't matter, it's not going to go back. It keeps actually getting what? Away from the equilibrium point and never going back. So we can say this guy is what? This is an unstable equilibrium point. Now the question is, can this stability or instability be determined mathematically using what we know in mechanics? And the answer is yes. The way to go about it is to look at the potential energy, P, and the variable of interest or variables of interest Q, a generalized coordinate. If the first derivative of P versus Q at the equilibrium point is 0 and the second derivative is positive, then that equilibrium point is a stable equilibrium point. On the other hand, if the second derivative is negative, then we can call this what? An unstable equilibrium point. Okay? Now, why is it that in both cases you see that the derivative of potential energy with respect to Q is 0? Because the derivative of potential energy with respect to the Q is actually what? That is the conservative force. That is the force of like gravity, spring, or any conservative force. You know the potential energy of that when you take the derivative with respect to that variable, that's the conservative force. For example, for spring, the potential energy in the spring is 1/2 kx squared. And if you now take the derivative of this potential energy with respect to x, it is going to be negative kx, which is what? The force of the spring. Correct? Or for gravity, let's say the potential energy in gravity, P of G, is equal to negative mg times y. And if you take the derivative of, or positive mgy actually, if you take the derivative of this P of G with respect to y, that is going to be mg, and this is what? This is the force of the gravity in magnitude. So when we say it is 0, that means that force is equal to 0, and of course we know that's the first condition for something to be an equilibrium point, right? That the forces, some of the forces should be what? Equal to 0. So here we assume that the potential is coming from that conservative force, and that force is the only acting force on the object. So when that guy is 0, the forcing function is 0, then the system should not move, so the system will stay at what? Equilibrium. So that clearly comes from the notion of equilibrium. The forcing function should be 0, right? And why is it that this second derivative, positive versus negative, makes the difference between stability and instability? Well, that's because of the chain in the potential energy would tell us something. When you change your variable Q, and that makes what? That makes the potential energy, the derivative of potential energy, to be positive. What does it mean? That means if you look at the curve is going to be like this, right? This is a convex function, right, with a positive second derivative, positive curvature. And what's going to happen here? Well, if I change the Q a little bit, right? So I'm here, that's my Q of the equilibrium point, Q star, you might call it. And now if I go ahead and change, and this is the potential energy that I have, P star. Now if I change my Q, what's going to happen? When I change my Q to any side of that equilibrium point, that means your potential energy, if you look at it, is going to go bigger than what it was at the equilibrium. It doesn't matter you are on which side. On either side, if you are, you can have what? A bigger potential energy. And how would you gain potential energy? Well, if your system is at equilibrium, means it does not have what? Kinetic energy, right? There is no kinetic energy. So the only way that you can gain potential energy is by doing work, right? So at equilibrium, K is 0. If your delta P is positive, like this case, you gain potential energy. That means the work that you should do on the system is positive. And that's not how the nature works by itself. If you are not interfering with the system and let the system act naturally, the nature will never work in a way that if it doesn't have to do any work to get its job done, it does. Okay, there is something that is called principle of least action, right? So let me write it for you here. It is called principle of least action. Mathematically, you show it as integral of variation of integral of L dt. Well, L is the Lagrangian, is equal to 0. But if you want to express it in plain English, the plain English is what I guess this founder really of this principle said, the scientist Maupertuis. He said, and I really love this quote from him, he said, nature is thrifty in all its actions. Okay, so if you leave nature alone, it's not going to act or work in a way that it has to do some work if it doesn't have to. Right? So this system, you're trying to force it out of equilibrium, but that means it has to do some work. And you say, well, I don't want to do it. I want to go back here when I don't have to do any work. So it goes back and becomes stable. While on this side, what's going to happen here? When you have negative curvature for P versus Q, your potential energy looks like this, right? This is the concave function. And what you have here is if I move my point from the equilibrium point, so again, this is Q star, if I move it to either side, doesn't matter, your potential energy drops. So here, this was your potential energy at the equilibrium, and the, oh, I forgot that I shouldn't clean everything like that. And the potential energy at the new point is something like this, which is less than P star. So in this case, your delta P is negative, and when K is 0 or delta K is 0, that means the system does not have to do anything. Actually, what it needs is a negative work. Or as I said here, what it does is to release some of its potential energy, and that's how the nature works. If nature can release some of its potential energy and doing no work, it is willing to do so. Another way you can describe this principle of least action is in nature, the systems would like to get to their minimal potential energy. Again, I explain it this way. In nature, systems would like to achieve their minimal potential energy. That's an energy that is potential, and the system would like to release it. So if you let this object go from here to here, it is already released some of its energy, and the further it goes, the further it releases some of that energy and get rid of it. So it is willing to do so and get away from that equilibrium point. That's why it is considered what? Unstable. So hopefully it is clear why these two formulas are there for any equilibrium point. Now, to show you in action, to show you the use of them for some well-known problems, especially the pendulum and inverted pendulum, I'm going to apply it to a couple of examples here. So the first example, as I said, is pendulum and inverse pendulum. And what I have here is a rod without any mass, but length L, and then I have a concentrate mass of M here. I call this angle theta. And what I will do, I will calculate the potential energy of the pendulum with respect to a datum, and then we take derivatives. So here, if I consider the very lowest point of this pendulum, the pedigree, you might call, right? So if this length here is also L, if I put my datum of potential energy right here, where P is equal to 0, okay? So this is the datum of the potential energy. Then if this change in height, I would call it Y. The potential due to gravity, which is the only potential you have here, is going to be what? Is going to be m times g times y, right? Especially because this y is what? Positive. It's about the datum. Now, how much is y? It is a function of L and theta. You know from your trigs that this y is going to be L minus L times cosine of theta, right? Because this guy here, from here to here, this is L cosine theta. And the whole thing is L, so the difference between them is L minus L cosine theta, or you can also factor out L out of here. It's going to be mgl times 1 minus cosine theta. So that's your potential energy. Now here I take the derivative of the potential energy with respect to my variable theta and set it equal to 0. The derivative of this function with respect to theta, it is going to be mgl times sine theta equals 0, and clearly it has two solutions. One of them is theta equals 0 degrees, the other is theta equal 180 degrees, which clearly give me both of the equilibriums, right? The equilibrium at the bottom and the equilibrium straight upright, inverted. Now the question is, between these two, which one is stable, which one is not stable or unstable? And to answer that question, I need to what? Take the second derivatives of P with respect to, theta. So let's do that. I take another theta derivative from this. I will get mgl cosine theta. Now at theta of 0, how much would that be? Cosine of theta is 1. It is going to be positive mgl, of course. It is a positive number. And at theta of 180 degrees, what would you get? Cosine of 180 is negative 1, so you will get negative mgl, which is negative. So that means what? It means this point here is stable, because it's positive, and this point here that got negative is what? Unstable. So you see, it correctly predicts which one of these two configurations of the pendulum is stable or unstable. What are the equilibrium points, first of all? You can get it from here. And then which one is stable, which one is not stable, you can also get from the relation between P and theta. Now here I would show you a second example where you have a system of rigid bodies. Here you have two rigid bodies, let's say C and BC. B is attached end of it to a roller that rolls on the floor, and it is also attached with the spring to a fixed support. The angle of both members are alpha because both of the length are L. Now this system at this moment with some alpha bigger than 0, with some magnitude of alpha bigger than 0, it is at equilibrium because these two members have m's. Let's call the mass of each member m. So they have mg's that they want to drop, right, and bring them down, but this spring is pulling back, and the combination will have what? An equilibrium, right? So if somebody asks you what is alpha here, and then is this equilibrium position stable or not? Okay, so alpha is what, and then whether it's what? Stable or unstable, which means if I just change alpha a little bit, right, or move this point B a little bit to the left or right to change alpha, is the system gonna completely drop and alpha gets bigger and bigger, or no, it might just move a little bit up or down, but then it goes back to what? to the equilibrium. At best, if there is no damping, it's going to start vibrating around the equilibrium point, but it never gets bigger and bigger, right? So here we assume both members have mass m, and the question is, what is the amount of equilibrium based on everything else? What is the angle, and whether it's stable or not? So let's take a look at that. Okay, so here we assume that when the angle alpha is equal to 0, both members are horizontal, the spring is at unstretched length. So let's add that here, and we say spring is unstretched at alpha equals 0. So the datum for the potential energy of the spring, right, P of the spring, is measured from that unstretched position when alpha is 0, and you compare it against the current length that the spring has, or the displacement of point B, which is going to be the change in length of the spring, basically. So if you know, the potential energy in the spring is 1/2 of K times S squared, right? Where S here is the deflection at that point. So measuring it with respect to unstretched position and alpha of 0, at this moment, the displacement of point B, the horizontal displacement of point B, is how much? So when alpha is 0, if I say what is the position of B, let's put our origin here at point A. So this is the y-axis and this is the x-axis. So if I say what is x of point B, well, both of these members with length A are horizontal and they are aligned horizontally next to each other, so it is going to be 2L. And then when alpha is arbitrary, right, then x of B, or you can call it x prime of B, or you can call it x of B prime, the new point, that is equal to what? So each portion of this basically projection, AC projected on horizontal axis and BC projected, is L times cosine alpha. So there are 2L cosine alpha, so this is going to be 2L times cosine alpha. Therefore, the potential energy, which is K over 2S squared, S is here, is the change in position of point B. So this is going to be x of B minus x of B prime, the whole thing squared. So this is going to be K over 2 times 2L minus 2L cosine alpha squared. And here there is a 2 that you can factor out, and there is L that you can factor out. When you square it, it's going to be 4L squared. A 2 of that will be simplified, so you will get 2KL squared times 1 minus cosine alpha, the whole thing squared. So this is potential energy of the spring in terms of alpha. Also, you need to look at the potential energy due to gravity here. And gravity, what I will do, I will also put the datum of potential energy here at the horizontal position of point A and B. So when the bars drop, they're gonna lose some of their potential energy, right? So if here is 0, at this point that they are laying downward, they have negative potential energy. And these negatives are what? They are equal to negative mgy, and you have to multiply it by a 2. Why? Because both of them have the same position for center of mass. and they have the same mass, length, and everything. So what you really have is this y here. That is the y of center of mass. And again, the reason it's negative, it's because it's below the datum. And how much is it? Well, the length from B to the centroid or A to the centroid is L over 2. The angle is alpha. So it is going to be L over 2 times sine alpha. So you will get a what? You will get 2 times negative mg L over 2 sine alpha. So you will get negative mgl sine alpha. Right? And now the total potential energy of the system is summation of the potential energies of spring and gravity. So it is going to be 2kl squared times 1 minus cosine alpha squared minus mgl times sine alpha. This is the potential energy of the system. Now to find the equilibrium points, I'm going to take derivatives. So first we look at the first derivative of p with respect to alpha, set it equal to 0 to find the stationary points. If I do so, the derivative of this guy, this 2 comes out. The derivative of negative cosine alpha is positive sine alpha. And this term would include a linear term, so it is going to be 4kl squared times 1 minus cosine alpha times sine alpha. And then this guy is going to be negative mgl cosine alpha. This whole thing has to be equal to 0. And now what you need is you have to expand it, or if you just look at it the way it is, you will have a sine term, you have a sine cosine term, and you have a cosine term. Okay, and this is a transcendental equation. This is not really a simple equation, but if you write sine and cosine in terms of tangent of half angle, that should hopefully lead to an equation for you here. So what I will do is I will use these two important relations, that sine of alpha and cosine of alpha in terms of tangent of half angle. This guy was 2 tangent of half angle divided by 1 plus tangent squared of half angle. And this guy is going to be 1 minus tangent square half angle divided by 1 plus tangent squared half angle. So here I'm going to apply these equations. If I call these equations set equations 2 and this equation 1, if I plug 2 into 1, that means by the way, I can get rid of one L term here because I don't need it. I will get 4kl, and it is going to be 1 minus this guy, right? So it is going to be denominator minus numerator, which if you subtract, you're going to get 2 tangent squared, right? And so let me write it down, 2 tangent squared of alpha over 2 divided by 1 plus tangent squared. This is the 1 minus cosine term. For sine term, I am going to write it again the way it is. So it is 2 tangent alpha over 2 divided by this term, and then minus mg times 1 minus tangent squared over 1 plus tangent squared. right? Now I can multiply both sides by 1 plus tangent squared to get rid of this denominator. And if you do so, then your equation will be, and what you can do, you can here also call your tangent of alpha over 2, you can call it x, or whatever you want, like call it z, for example. So z is equal to tangent of alpha over 2, then you will get what? You will get, here you have a 2, 4kl, so you will get 16kl, and it is going to be z cubed, because this is z squared, that is z, and then minus mg times 1 minus z squared. This is equal to 0, right? So what you will get is a cubic equation, and depending on what is k, what is l, what is m, you will have to solve for a specific number, right? A specific roots of this equation. So let's go ahead and in order to deal with some numbers, let's go ahead and plug in some numbers. So here, let's say for k, I assume this is like 100 Newton per meter, right? L is, let's say, 40 centimeters, and m is like, what, 1 kilogram, right? So let's plug in some numbers to make life a little bit easier. So L is, let's say, 0.4 meters, m is 1 kilogram, and your k is 100 Newton per meter. Okay, let's plug in these numbers and solve numerically, or we can use MATLAB in this case. So if we do so, this is 100, that is 0.4, right? So this product is going to be 40, and this m times g is just going to be 9.81. Right? So your equation is going to be 640 times z cubed, and then plus 9.81 z squared, and minus 9.81 is equal to 0. Right? This is going to be our cubic equation, and here I'm going to be using MATLAB. So here I'm using the command roots that solves it numerically, and you see there are 3 roots. 2 of them are complex, which they don't work here. The only non-complex for me is 0.2434, okay? So from here, your z, which is tangent of half angle, is going to be 0.2434. And from there, you can find your alpha for the equilibrium, right? So what I will do is arctangent d of answer number 3, right? And that is going to be, because that's tangent of half angle. So I have to multiply that by a 2 to get my alpha. And you see the answer is 27.36 degrees, right? 27.36 degrees. So this is the angle at which the system comes down to an equilibrium. Okay, now the question is whether the system is stable there or not. So what I need is to take another alpha derivative from p with respect to alpha, which is basically this function, right? So if I want to do so here, I would say my second derivative of potential energy with respect to alpha is going to be, and as I said, I need to take alpha derivative of this guy. This is a sine term, so it is going to be cosine. So you will get 4k L squared times cosine alpha. And the other term you have is negative sine cosine alpha, which is sine 2 alpha divided by 2. When you take derivative, you will get basically cosine of 2 alpha, right? Cosine of 2 alpha is cosine alpha squared minus sine alpha squared. and then you will have negative MGL cosine alpha. Okay, so this is what you get, and now you will plug this alpha into this equation and we'll see how much you will get. So 4kL squared, right? So this is 4 times k times L squared times, it is gonna be cosine of answer, and then plus cosine d of answer, the whole thing squared, minus sine d of answer, the whole thing squared, then minus m, which is 1 times 9.81 times L times cosine of alpha. Okay, so this is the second derivative calculated at the angle, and you see it is 90.32, which is definitely positive. That means the equilibrium is a stable equilibrium. Right? So hopefully going through this more complicated example and the pendulum could demonstrate this important rule that the first and second derivatives of potential energy with respect to the joint variable or variables is used to determine the location of the equilibrium, as well as whether they are stable or not. So I will see you in my next video. Thank you.